and the point is the topics we are reading is still I mean under the active research. So
Okay.
so that's why you see the problems are not very other numerical type problems, but most of the problems are from the lecture itself, or the derivation, or the whatever they have, I mean instructor have taught. So there
Okay.
are not really any it's not like other course where we have lot of numerical problems. The field is still developing. People, lot of people are still doing their research in the in all the domains actually: quantum hall effect, quantum spin hall effect, anomalous hall effect, everything. Okay, so we just wait for few minutes if others
Okay, sir.
join, and then we'll start.
Okay.
Okay, so I think other people may not join, so let's start.
Ye-
So if you have any questions or any confusion, let me know. That I will
Yes,
try to
sir.
address fast.
Yes, sir.
Hmm.
सर, beside the lecture of बसु सर,
Hmm.
ही था, उन्होंने बहुत अच्छे से एक्सप्लेन किया,
Hmm.
तो उसी के कारण कुछ और इंटरेस्ट बढ़ा, मैंने कुछ रिसर्च पेपर भी पढ़े.
Hmm.
तो इन दैट रिसर्च पेपर द टॉपिक रशबा स्पिन कपलिंग, उन्होंने ही बोला कि द मीनिंग ऑफ कपलिंग इन दिस topic is means their angular spin and linear spin lock. That type of terms they have used.
Right. Hmm.
So, and coupling, what I understand as a layman in this topic, that couple means addition. So, and in mathematical part, sir is also taken Sx, Sy, and cross product.
Hmm.
And cross product means the product is, suppose X and Y, we product two things, then the outcome will be along Z direction. So,
Hmm.
what is the exact meaning? That means two types of are cross producting, and then the product is perpendicular to that. So, what is exact meaning of coupling? Means is it a addition or it is a cross product? And what is the meaning of angular momentum and linear momentum? They are log. So that is my first question.
Okay. for the Rasba Hamiltonian or Rasba system, we have a Hamiltonian like simply p square by 2m plus alpha p cross sigma, let's say, and dot z cap, right? And this we call spin orbit coupling strength. Now here, here, as the name suggests, spin orbit coupling. So sigma represents the physical spins of the system. Unlike the graphene system where we had pseudo spin, graphene Hamiltonian was something like, let's say, h bar vf k dot sigma, or simply vf p dot sigma. In this case, sigma is the sublattice degree of freedom. This was coming because of they have, I mean, graphene, we have two sublattice A and B, right? So if you draw this graphene structure, then the Brillouin zone for graphene would look like this kind of Brillouin zone where there will be K and K prime. In the real space also,
Yeah,
the unit cell
linear,
consists
linear.
two types of atom, A and B. This is A and
Yeah.
B. This was for graphene. Now in Rasba system, we have a, so this we can call it actually orbital and sublattice coupling. So orbital we just mentioned because so the momentum essentially coming from the orbital motion, or momentum basically dictates the orbital motion of electrons. Okay, uh, that's, so this, in this way we can say that this is orbital sublattice coupling, but there is nothing as such special coupling in this. It is just there in terms of Hamiltonian. Around the low energy we can write. And here we, when we say that spin orbit coupling, we can think that P is representing that orbital motion of electrons, and sigma is the physical spins of the system. So they are coupled. In graphene, you didn't have any spin orbit coupling strength, sorry, spin orbit coupling in the system, although it has actually in graphene, but we do not consider because graphene spin orbit SOC strength is 10 to the power minus 6 SI unit, let's say. Okay. If we, in terms of
Okay.
energy, 10 to the power minus 6 joule, let's say. Yeah. But this is actually very small. Okay. So that's why we do not consider spin orbit coupling in graphene, but in other system where the proton number is high, that means the Z atomic number is high, then there can be intrinsic spin orbit coupling, which is significant uh, than other materials like graphene. So there, it basically represents the spin and orbital are not individually uh, commutes with the Hamiltonian. So if I have this, let's say sigma is the spin representation or spin angular momentum, because S is the S has a unit of, or S is given by h bar by 2 and sigma, right? And h bar has a unit of angular momentum, right?
Okay.
Angular momentum, and this we can easily understand because from the first atomic forces we have that angular momentum mvr. This was the problem of hydrogen atom, Bohr radius and all those concepts were covered, is quantized in units of h. Let's say n is the quantization number and h is the Planck's constant, and h bar is nothing but the h
H
Planck
by 2
constant
pi.
by 2
Yes.
pi. So so basically this h bar is unit of angular momentum. So whenever we say, right, s is representing the spin angular momentum, and this we do not want to think, or we cannot think in terms of classical analog, because spin do not have any classical analog. For example, we have some particle, let's say, and it is moving in some circular motion, then we have a linear angular momentum as well as the rotational angular momentum L, right? Because of
Okay.
this rotational motion, which will be pointed outward. Now, and this will be, let's say, linear angular momentum mv. And now spin are some objects which is intrinsic to the electrons or fermions, let's say, in fact other particles as well. This do not, we cannot, we should not really actually think any classical analog of this. This is intrinsic nature, and this purely comes out as a uh, I mean quantum mechanics of the electrons. Uh, so what really happens is that we tend to think quantum mechanics and so on in terms of Schrodinger equation, right? We had some Hamiltonian, and we have wave function and some eigenenergy. This we can even write as h square by 2m grad square. This is in real space, and plus v of r, some potential, and then psi of r, and then energy and psi of r. Right. This is Schrodinger equation. Let's say uh, here we need to explicitly put the spin degree of freedom by hand, that my particle represented by this psi r wave function is of spin up or spin down and so on. Spin information is not intrinsic to this Schrodinger equation, but when you consider Dirac equation of relativistic particle, electrons are end of the day relativistic particle. So then you will have this spin construction or the spin nature of the electrons intrinsically. It will follow intrinsically. We don't need to put spin information out from the outside. So, and this is one of the way to understand that we should not think of any classical analog of spin. So nonetheless, the main point is ki, similar to this angular momentum concept, which you can think of any classical particle, right? If any classical particle rotates, it will have some uh, linear momentum as well as angular momentum. Similarly, spin has some intrinsic momentum, which we call spin angular momentum. Spin angular momentum, which is clear from this expression, because h bar is a unit, has a unit of angular momentum, and sigma is the Pauli matrix represented for, that we can represent for 2 by, spin up and down. And if you see this expression, so we have actually alpha p cross uh, p cross sigma, but indeed we can write as alpha by, let's say, h bar, and then p cross s, right, and so on, and this was z dot, so z dot. So so this is linear orbital motion represented by this p linear momentum, and this is angular momentum of the spins, and these sort of couples to each other, then we call this spin orbit coupling. Okay, which is coming due to the so when we consider the electron's rest frame, then we kind of can visualize that electron experiences some effective magnetic field because of proton and so on. When we so we have some proton, let's say, in an atom, and we have lot of electrons and some protons in the nucleus, but so whatever we think usually is in the rest frame of some laboratory frame, but what will the electron experience? If we want to fully understand that what the electron experience in terms of, let's say, electromagnetic field, then we need to go to the rest frame of the electron, means we are also rotating with the electrons, so there is another frame which is electrons frame. Now from this frame, it will appear that protons are moving, not the electrons, in the electron system, just like we usually experience while moving on train.
Yeah.
And from this, so any moving particle, any moving charge particle emits or creates electromagnetic field, right? Moving charge particle, and that's according to actually classical uh, electrodynamics also. Moving charge particles create electromagnetic field. Now, from this concept, Professor Basu derived that what should be the effective field that an electron experiences due to, let's say, proton and other thing. And again, so if you really so carefully observe that whatever we did in term while deriving the Rasba spin orbit coupling or the effective magnetic field that an electron experiences, we only took into account of the classical electrodynamics, right? We didn't have considered any quantum electrodynamics. And from that we considered, I mean, we kind of derived that effective magnetic field is simply given by V cross E by C square, where E is the some effective electric field, let's say. Now, this actually gets corrected later. I think Dirac or someone else proved that the this effectiveness of considering the classical electromagnetics uh, while deriving the how much magnetic field, effective magnetic field electron experiences due to proton is almost same, but it is off by a factor of 2, which we call gyromagnetic ratio, G equal to 2. So form remains same, expression remains same, but we just miss a factor of 2 while deriving this thing. Okay, so Hamiltonian for this will be, this was mu dot B, right? Spin orbit Hamiltonian. So B is the effective magnetic field and mu is the magnetic moment of an electron. And this is again related to the S, let's say G. This is again related to the spin of the electron. So this is mu dot B, and here mu extra 2 factor G equal to 2 factor comes as a, we can think of as a quantum correction. We have derived everything in terms of classical electrodynamics, but that doesn't give me the correct answer. Nonetheless, it gives me correct form. So when I do full quantum theory, we just get a correction term. Everything else remains finite, I mean same. So so uh, from this actually we understand that we can think of this as a spin orbit coupling, because there is a coupling between the orbital motion represented by P and the spin of the electrons represented by sigma. So the simple explanation would be this: actually spin orbit coupling means there is a coupling of the spin motion and orbital motion and spin degree of freedom of the electrons, and that's why we do not have any uh, I mean, the Hamiltonian doesn't commute with the spin degree of freedom whenever we have spin orbit coupling.
Okay, sir. I understand. My next question is one word is this type of topic hold true only for inversion symmetry, or some research papers said 180-degree symmetry. So inversion symmetry means it is a sort of mirror image that I read, or something else. Sir, give the example that graphene is in between graphene and substrate, air is there, and all that. So, what is the exact meaning of inversion symmetry? That topic hold true only for inversion symmetry.
Oh, so
So,
it turns out that the spin orbit coupling that we talked about, or the simplest way to understand how spin orbit coupling arises, is that Rasbach spin orbit coupling term. What we have just explained, that we go to the electron's rest frame and see how much of effective magnetic field kind of electron experience due to positively charged protons in the nucleus, and from there we derive the expressions of effective magnetic field, effective electric field, and the correction that it induces in the Hamiltonian or in the dynamics of the electrons that we need to consider, right? And the correction term would be, so again, this correction term essentially comes from this mu dot B, and the physical way to understand is that this this is because in the presence of magnetic field, spins would like to kind of align with the magnetic field, right? If this is the direction of magnetic field, if this is the direction of spins, then if they align, their energy gets minimized, minus mu b. If they are not aligned or anti-parallel, then they will have energy of plus mu b, which is higher than this minus mu b, right? So from this, again, this can also be derived. Actually, we have not derived, but effectively from this we can arrive that alpha spin orbit coupling strength and z cap cross k dot sigma where alpha is E electric field, effective electric field, h bar square, 8 pi square m square c square, and then yeah, that's it, extent of the spin orbit coupling. Now, when you do symmetry analysis, it turns out that in a material, if this term needs to be finite, then we must need to break the inversion symmetry, or it can only appear in the yes, so it can only appear in the inversion asymmetric system. What do we mean by that is that inversion symmetry, sometimes we also call it parity symmetry, maps a point r in the crystal to minus r. Okay, so suppose I have a some unit cell of a crystal, and this is the center of the unit cell. If this environment of r and this minus r, and this is the origin, let's say, if it is same in all direction for all r that you can think of, or that can be there in this unit cell, if the environment or so I go to r point and I go to minus r point, if the chemical composition and other things are same, then we call it inversion symmetric system. That means if I do a inversion of the point, so minus r is nothing but the inversion operation, right, of r point. So if it is same composition and same thing, then it is inversion symmetric. And it turns out that this term vanishes in inversion symmetric system. So hr equal to 0 in inversion symmetric system. And one easy way to understand this is that, since so this is in the real space picture, that r goes to minus r, my system chemical composition and other things should remain same, and that's why we call it inversion symmetric system. If we just go to the Fourier space, which is the reciprocal space or the momentum space, all the names are I mean, we call it reciprocal space, momentum space, k space, all are means same. There also uh, the k point in the momentum space maps to minus k point in presence of inversion symmetry. So let's say if we are talking about energy is a function of crystal momentum k, if this is the case, then it is inversion symmetric. So in real space, you think of the chemical potential, position of atoms, and so on and so forth. Whenever we around the origin of a unit cell, you just do reverse of operation. I mean, r goes to minus r, and in the reciprocal space, you just take the Brillouin zone, okay, and see that the band dispersion and other things are symmetric in k or not with respect to the origin of that Brillouin zone. We don't need to think about all the crystal, I mean, so any solid state system is basically composed of lot of unit cells, right? Unit cells are defined in such a way, the definition is such that we have a structure. If we can fully get the whole lattice system, whole solid state system by repeating the same unit cell, then it is called unit cell, otherwise not. So all the symmetry information and other things are only I mean, we need to only consider about on the unit cell only. If it is symmetric in one unit cell, it should be symmetric in the system also, because that's how the unit cell is defined. So in the k space, this is the this is in terms of energy, it reflects this way ki, at k point and at k minus k point, the system is I mean, the system's energy is same. If it is so, then we call it inversion symmetric, and if it is not, then it is not inversion symmetric actually. So now coming to this inversion asymmetry of this Rashba system, if you do the operation HR under inversion symmetry, which is let's say I cap inversion symmetry operator, then it will be alpha is some constant spin orbit coupling strength, and this k, z cross k, z will not change, z is just representing the direction, nothing else, and cross this will be minus k, k goes to minus k, and dot sigma, sigma doesn't change because sigma represents physical spins of the system, and spins do not change under the inversion symmetry, rather it changes under the time reversal symmetry actually. So k goes to minus k, and this will be minus of hr. So what really happens is that hr of k, hr of k minus k, sorry. So whenever you operate inversion this operator, then it becomes hr of minus k, right? Because k goes to minus k under inversion, and this effectively becomes hr of k minus we have taken out. So so this represents that in inversion symmetric case we do not have this kind of relation epsilon k equal to epsilon of minus k. So that means that Hamiltonian Rashba Hamiltonian, the Rashba term is not compatible with the inversion symmetry. That means, in other words, we can say that in inversion symmetric system it cannot appear. Okay, this becomes a bit mathematical, but that's I think the easy way to understand that in inversion symmetric system the Rashba Hamiltonian cannot appear, or the Rashba spin orbit coupling cannot appear. I hope it is clear.
Okay, sir, it is clear. Sir, another thing is that the equation of continuity is different from this system. Something change. So, what I have read, equation of continuity in electrodynamics that if entering flux is less and emerging is more,
Hmm.
that means that is only possible when density decreases with respect to time. That's where the
Yes.
equation is coming del rho by del t and plus divergence of that equals
Hmm.
to zero.
Hmm.
That is the concept. That it is what I thought that it is related to flux.
Hmm. Hmm.
So, but in this topic, sir is using equation of continuity for this system, and it is change. But is there any description of or involvement of flux or that type of thing in this, or it is a different thing?
No, flask. When you say equation of continuity of a flask, it doesn't say flask of what, right? In fact,
Yeah.
the construction of continuity equation is simply flux of some particle, flux of some, let's say, magnetic field or anything else, any vector field in general. If you go abstract mathematics term, then it is any vector field. Here we can think of that the flux is of electronic velocity or electronic charge, let's say, right? So the for charge current, what really is the if I use the notation of Basu sir, then del rho L del T plus gradient in real space J electron equal to 0, right? That's what the equation of motion.
Yes.
It says that rho EL is the charge density, and JEL is the current density. Now it says that uh, let's say we can also write rho EL del rho del T equal to minus of divergence of JEL. So it actually represents, so this is the current, that means some electronic particle are moving, which is represented by J. And J, what is the definition of J? J is the current per unit area, right?
Yeah.
So current means what? Uh, Electrons and then velocity. Yes. uh, or we can also write that some charge that is going on by per unit time, and this is area. So this we can actually think of the flask of the electrons or any charged particle, let's say, in general. So this is representing that current, and we are taking divergence of that. That means again, whatever you are calling that flask concept is already coming whenever we are taking divergence. and this reduce, or the when this negative sign represents that the change of electron density at some point. So we fix some points or volume, let's say. The change of electron density is given by this current flux or electrons flux, and this electrons flux actually represented by JEL. You get only current when electron moves, right? So let's say from this volume, hypothetical situation, from this volume, we are generating current. So we are essentially losing some electronic charge. So del rho del 2 is negative because we are losing with respect to time. And how much we lose, it is represented by this divergence of JEL. So the concept remains same actually.
Okay.
Okay. And for spin also, will have similar kind of way.
So equation is changing, but concept is same.
So
That
this you can think of electrons flux, JEL representing, or divergence of JEL representing electronic flux, let's say, and del rho EL del T represents the uh, change in the electronic density. So this will be when you do volume integral, it will be more clear, right? Volume integral del rho EL del T, and then minus divergence of R dot JEL, and then volume integral. From this we will see. I mean, we can show the things are actually equivalent.
so that means in this topic the theorems also applicable. Like in class, previously we have read that Gauss divergence theorem, Stokes theorem.
Right, right.
That
This
we
is
can
applicable.
applicable in a spin concept also.
Spin concept. Okay, so you are talking about spin current, right?
Yeah, that here we have studied spin that even and odd are distributed, and sort of new current is produced. Uh,
Mm-hmm.
so that type of phenomena we have read in our lectures. So if continuity is same, then we can prove Maxwell's fourth equation by equation of continuity. That type of derivation we have studied by equation of continuity, Maxwell's fourth equation, then vice versa. So
Mm-hmm.
for that means that type of Maxwell's equation, they are also applicable or have some new version of these equations.
So, okay, Maxwell's equation.
One derivation I have read that Maxwell's fourth equation by equation of continuity.
Mm-hmm. Okay.
So if equation of concept is same, then we can also prove in this concept also all these equations.
Yes, yes. Right.
That
In
is my
principle, we
my
can do.
opinion. That is my opinion. I'm not 100% correct.
No,
Maybe
so
incorrect.
we are not really. So even if you do full quantum, I mean, construction, there also we have concept of continuity equation and so on. So that you can do. Now, I do not understand your questions, but how you want to connect Maxwell's equation actually. Maxwell's equations are there independently to explain the classical electromagnetism, right?
Yeah, yeah.
So there you will have continuity equation of charge, continuity equation of other things, and so on. Here we also have continuity equation of electrons, which represents that. Uh, I mean, the basically the relation between the current density and the charge density of a particular area or volume, let's say the
Uh,
so.
because uh,
Hmm.
because in Maxwell's fourth equation, the basis of proof is that by equation of continuity, it testify the equation by equation of continuity. That this equation is not whole true. That's why correction term is needed, and then he had the correction term and makes the new Ampere circuital law and all that, and then define the Maxwell's fourth equation.
So
So basis equation of
you are talking about this equation, del E del T.
yeah, yeah, yeah.
Okay, so there, I think this was the initial part, and then
The
I
correction
think,
term, that is,
right,
that's
Michael
correction term.
Faraday came and say ki,
Yeah, yeah.
no, we need some extra term because of,
Yes, yes. So
uh,
basis of this equation is equation of continuity
right, right,
to testify this. That's
right.
why what I'm really, I don't know that I'm communicating you or explaining you correctly, or you can understand my
Here
thoughts.
also, you will have the equation of continuity kind of thing.
Yeah.
I mean, again, the basics of, actually we should not call even it is the basics. The basics is the continuity equation. The basic is not the continuity equation. The basic is the conservation of charge or conservation laws. Let's not restrict only to charge. It can be charged, any particle, or any other thing. Let's say. So that is my fundamental point, that I need to conserve things if it is conservable item. For example, spin is not a conserved quantity in presence of spin orbit coupling. It is not conserved quantity because spin can change its orientation, up, down, up can go down, down can go up in presence of magnetic field, or in presence of, not even in presence of magnetic field. If you have a spin orbit coupling, then spin and orbits are coupled. So up spin can be down due to dynamics of electrons and so on. So in that sense, spin is not conserved, but how many number of electrons, if I have a closed system, and the number of electrons must be conserved, right? If I'm not losing electrons within that closed system. So my basis is the conservation theorem, and the result is the different continuity equation. In classical electrodynamics, you will get some, here in terms of current density or electronic charge density. In other field, you will see other conservation theorem, right? As for example, in fluid, we will have different kind of continuity
Yeah,
equation.
yeah.
So again, all of those basics lies in the conservation theorem, and we get different forms, different manifestation in different physics
But
phenomena.
here we meant only, or we are taking only for the showing the conservation of charge.
Right, right.
Okay, okay. But there may be future research aspect of this
Mhm.
to club these topics to Maxwell's equation and all that. That may be future research topics, I think.
No, actually, those are already clubbed as far as my knowledge goes. Most of the cases,
Okay.
classically, whatever we can do, we did quite a bit. I'll not say everything because in research, nothing is, I mean, nothing is the end. But so this kind of explosion is already there. We just uh, do not write in terms of again and again those continuity equation and so there, it turns out that there are a lot of different representation to study the charge, current, and other things. For example, you studied Kubo formula in these classes also. There are semi classical formulation, there are quantum kinetic theory formulation, and so on. And all of those basics remain same. We need to have charge conserved and so on, and all these theories are actually consistent. We can show by some mathematics that indeed because those theories are actually based on those basics assumption that charges are conserved, electron carries charge of minus e, and so on. These are just different ways to converge on the same result, let's say. Okay.
Okay. Okay. So these are only my doubts that you cleared very well.
Okay, so in the last class there was a guy Sanam. I think he asked me to uh, do or say few things about the Subnikov-Diaz oscillation, but it turns out that he is not present.
No, nobody is there.
Hmm. So if you are interested, I can present the Subnikov-Diaz oscillation. It will be at least recorded, and if you wants to see, then I can see.
Yes, sir. I am interested.
Just a second. Uh, so let me stop sharing this one. Okay, you can see the PPT slides, right?
Yes, sir. I can see.
Mhm. Yeah. Okay, so Subnikov-Diaz oscillation is basically the oscillation of longitudinal resistivity. So far, we are actually interested in the resist. I mean, Hall plateaus, quantum Hall effects, let's say, right? So, quantum Hall effects means at particular interval of magnetic field, we have Hall plateaus where the with the increase of magnetic field, the resistivity doesn't change, and after a certain magnetic field, it again increases and again it decreases, and so on. So that was the transverse component of the response. What it means is that we applied, let's say, electric field along the x direction, and we are measuring the voltage along the y direction. So it is perpendicular to the x direction. Meanwhile, the magnetic field was applied in the z direction. So mutually perpendicular configuration. Electric field in x, voltage measured in y, and magnetic field in z direction. And in that plot itself, so if I show you, we if you noticed, we have seen there was another plot of oscillating kind of resistance which was linear. uh, so so if you take this plot itself even, uh, so you're able to see my screen, right? Hello.
Yes, sir. I am able to see.
Okay, so if you look at this figure itself, then this red color is the representation of rho xy, which is the quantum Hall effect, or quantum Hall resistance or resistivity rho. This is the red curve, and then rho xx is the longitudinal resistivity, which means that I applied electric field along the x direction, and magnetic field is as usual along the z direction, and also I am measuring the voltage along the x direction itself. Hall voltage is along the y direction, and longitudinal voltage rho xx is along the x direction. And this is represented by this longitudinal resistance is represented by this green curve. And as you see, initially it was kind of constant, and then it start oscillating back and forth, and then it shows clear signature of oscillation. Here in this region also you will have oscillation, but it is kind of overlapping. You need to zoom in to see it. But again, nonetheless, the oscillating signature is clearly evident. So this oscillating signature is actually, I mean, can be understood by Subnikov-Diaz oscillation, or what Subnikov and D has explained why this oscillation arises. These are two scientists, Subnikov and D has. So, so this will let's understand why this arises. And these are some preliminaries. Let's go through it quickly. So let's say we have a two-dimensional electronic uh, gas, that means electronic system in a magnetic field. If we have magnetic field, then we have some Lorentz force acting on those electrons, which can be represented by this m dv dt minus e v cross b. This is again classical electrodynamics. This is kind of in the real space picture. In the k space picture, if I go, or the way we representing things, everything in terms of k crystal momentum, so this will be given by h bar dk dt, which is again force, and then same expression minus e v cross b, Lorentz force basically of the electrons. And the electron's trajectory, remind we are talking about free electrons, the electron's trajectory in both the real space and momentum space looks like this one, circle. In k space also it circles, and in real space also, uh, because of the magnetic field it circles, I mean, which we call cyclotron motion. Now, if we have, we have for free electronic gas, we have h bar square k square by 2m, which is the Hamiltonian for two-dimensional electronic gas in presence of magnetic field 0, and we have the band dispersion like this, kx square plus ky square, which is a parabola actually, right? We have not shown any parabola here, but the important point is this is a continuous spectrum, right? Kx, ky do not have any constraint. It can just increase continuously as represented by this figure b equal to 0. It can have any epsilon, delta epsilon, again epsilon, delta epsilon, plus delta epsilon, and so on. So basically this is continuous. And what it really happens when you apply sufficiently high magnetic field, so that there is a complete circular motion of the electrons, I mean cyclotron motion, complete circle forms there. In k space we can have Hamiltonian like this we have already done quite a few times. This is nothing but just the Peierls substitution. Momentum goes through some modification. A is the vector potential, where curl of A is given by the magnetic field. And if you solve this equation again, this is a well-known equation, uh, the Landau levels forms basically n plus half h bar omega c. So this is for the free electron gas, and the dispersion is independent of k, and this looks like this kind of dispersion relation we have. Kx, it is independent of kx ky, it's kind of full circle, and we have energy, as energy increases as we increase the quantum number n equal to 0, 1, 2, 3, 4, it increases, it's keep increasing basically. So this was the case of 2D electron gas. I'll parallelly go through 2D and 3D so that things becomes more complete. Now, in 2D, we only assume that we have 2D electron gas in the xy plane, and we apply magnetic field in the z direction. So there is a circular motion in the plane, right, in the xy plane. In 3D, what really happens is that we apply magnetic field along the z direction, but now the electrons are not confined to the 2D xy plane, but it
So,
can
sort of helical shape. Helical.
right, it can move any direction, not only kx ky. So so the direction, in the direction of magnetic field, we have a kind of helical motion, and in the direction perpendicular to the magnetic field, so this is the plane, let's say, we have again circular kind of motion. This is for the 3D, and we can similarly write the Hamiltonian also. The only extra term will be h bar square kz square by 2m. And the important difference is that in 2D case we have a Landau level flat, right? When you plot with respect to k, because it has no dependence on the kx and ky. This was the eigenenergies in presence of magnetic field. But in 3D we have Landau quantization or Landau quantized energy levels like this. This was purely kind of 2D, right? N plus half h bar omega c. But due to extra degree of freedom along the kz, we have parabolic dispersion along the kz. So the important point is, in whichever direction you apply magnetic field, we have applied magnetic field along the kz direction, it doesn't affect the free electronic motion along the magnetic field direction. Whereas in the perpendicular direction, it just creates similar Landau level, similar cyclotron orbit like the 2D case. Now this energy can be represented as Landau tubes. In the next few slides, it will be clear that why we want to
Hello.
construct this. Yes. Uh, yeah. Question. Hello.
I think Sanam is joining.
Yes, yes. First of all, sorry for joining. Yeah, yeah. First of all, sorry for joining late. I was actually
No,
stuck
it's okay.
in somewhere.
Hmm.
So I have a very basic question actually.
Hmm.
Hello.
Yes, you are audible.
Like, can we okay? Can we get to see quantum Hall effect in 3D electron gas?
Oh, that's a very nice question, and I do not have an immediate answer to this. The reason is the following: I know partial
Okay.
answer to it. Uh, I know that theoretically there are quite a few proposals, but experimentally they have been observed or not, I'm not sure. In
Okay.
fact,
Okay.
I was one of the reviewer of one of this project, I mean paper, 3D quantum Hall effect, few days back, few months back. They
Oh,
did
so
a
it's
nice
like an
theory.
open area.
Yeah, yeah. So all of those
Okay.
things
Okay.
are actually open. Even quantum Hall effect
Oh,
is
so
fully
it's like
understood,
somewhat
probably
like
not.
okay. Okay.
Yes. So the quantization actually in conventional sense is killed by
Okay.
this h
Okay.
bar square kz
Okay.
square time, right? Because you have some perfect plateau, and there is kind of something is stop increasing,
Yeah.
right? Resistance stops increasing further around a particular window of magnetic field and then starts decreasing, right? Those things are because of perfectly
Yes.
flat Landau levels and so on. There is
Yes. Yes.
a lot of calculation, but it can be shown. But eventually, that is the case. We have perfectly flat Landau levels and so on.
Okay.
Here, in this case, we have a continuous motion along the kz direction actually, and that in calculation we can show that that actually kills the perfect
Yeah.
flatness and so on. Quantum Hall effect, quantized plateau. Okay, we have other kinds of quantization in 3D system as well as 2D system, but again those are not quantum Hall effect, those are called anomalous, quantum anomalous Hall effect, and they are also the concept of edge states and so on comes, but in a different, in a little bit different context, in a little bit
Okay.
different way. And that too not always. If we have some insulating system and then if the
Okay. Okay.
insulator is quantum anomalous Hall insulator having non-trivial topological edge state and so on, all those things are there. Okay, so coming back to this,
Okay.
we can represent, or we represent this kind of Landau
Okay. Okay.
quantization for 3D electronic gas by this Landau tube. If we choose any particular nth energy, let's say, along this direction, z direction, we have we represent this h bar square kz square by 2m term, and then this area, let's say this xy plane area is represented by this h bar square k square by 2m kind of circle. Okay. And this kz can go to
Okay.
0 to
Mm.
and something which we usually have in solid state system. Okay, so and these are the kz 0 plane, and in this direction kz minus plane, I mean kz minus, and this is kz plus. So this is one of the Landau levels for a 3D electron gas. Now what really happens, so essentially we change magnetic field and see the response in terms of longitudinal voltage or in terms of quantum Hall, I mean transverse voltage. So what really happens to those energy levels when I keep increasing the magnetic field? If I increase the, as the magnetic field strength increases, the radius of the Landau tube corresponding to a particular Landau level increases. This is because we have represented that this xy plane motion by this representation h bar square k perpendicular square by 2m, right? And k perpendicular simply represents the perpendicular motion, I mean motion of electrons perpendicular to the magnetic field, which is xy. So as the magnetic field increases, omega c is proportional to b, so this k perpendicular will also increase, right? This is just simply so this part we are writing as h bar square k square by 2m, which represents the area in the xy plane. Okay, now if we keep increasing the magnetic field, k perpendicular representing the radius of the Landau tube for a particular Landau level for three-dimensional electron gas keeps increasing, right? And this circle represents the Fermi surface. I explained the notion of Fermi surface in solid state system. Let's say we are in zero temperature limit. We are indeed in very low temperature regime. Otherwise, you cannot see quantum Hall effect, quantum oscillation in longitudinal resistivity, and so on. So assume that all the electrons are within the Fermi level at perfect 0 Kelvin temperature. So this is the Fermi. Yeah. So this is the Fermi surface. Let's say. Okay. So let me use. Okay. So this is the Fermi surface. So as you keep increasing the magnetic field, the Landau table's radius keeps increasing at some particular magnetic field. This is going out of the Fermi surface, right? And this is not possible. What it really means that if this Landau tube goes out of the Fermi surface, that means outside the Fermi surface there are some electrons with energy of this corresponding Landau level at that particular magnetic field, let's say. But as we know that in 0 Kelvin temperature or in that limit, electrons can only reside within the Fermi energy, below the Fermi energy, right? So then what will really happen is that these tubes, whenever they exceeds the Fermi energy or the Fermi surface, the electrons corresponding to that energy is going to jump back to the lower level below Fermi surface. Okay. So this will create, or let me read this statement, which will be clear in the next slides, that the total number of states is proportional to the area of the portion of Landau tube contained between the constant energy surface epsilon and d epsilon, let's say. Now, what will happen is that for extremal cross section area, number of states and DOS attains a peak. The reason, since the number of electrons that can reside on that particular energy, on this particular energy, let's say, is proportional to this area, that we can show actually. Okay, I'm not showing the mathematics now. Now if the now for the extremal cross section area, which will be the equator case, the number of states and the density of states will attain a peak, right? Because this is the maximum that can be there within that Landau level in the 0 temperature limit. Whenever we increase further magnetic field, here it is with respect to energy, but again it is same under the magnetic field also similar. Then the Landau tube will go outside of that Fermi surface, and then those electrons residing on that energy will jump back to within the Fermi surface. So immediately there will be fall in the density of state, and then it will rise because of there are a lot of Landau tubes, means there are a lot of individual Landau levels within a Fermi energy. Okay, and this type of oscillation will keep going on. So uh, so let's try to understand it more clearly from this figure. So we had Fermi surface, we have Fermi level at t equal to 0, we had some Fermi surface, magnetic field is 0, we have continuous spectrum, continuous energy spectrum, right? Now we apply magnetic field of value, let's say V1. So there are perfectly flat, let's say Landau level. I mean, these are just representation. For 3D, it will not be perfectly flat, but nonetheless. So there are some Landau levels, and in each Landau level, there are some electrons that will reside from the low energy to high energy. It will keep occupying things. And then this is the situation at magnetic field B1. Now we increase the magnetic field, let's say B2. So what really happens is that the Landau level gap between the two consecutive Landau level is proportional to the, or is equal to the h bar omega c, right? And omega c is nothing but the EB by m. So as we increase the magnetic field from B1 to B2, the gap between the two consecutive Landau levels will start increasing. So what will really happen? So this Landau level will go higher, this Landau level will go higher, so that the gap increases between the consecutive Landau levels. So once this Landau level goes up, so this is the Fermi level, this is my Fermi level, EFT equal to 0. That means that these electrons of this state is going higher higher than the Fermi energy, which is not allowed in the t equal to 0 temperature 0 case. Then the only option that these electrons have is that they fall back in the next Landau levels or the next set of energy levels, which is below the Fermi level or at max at the Fermi level. So that is what happens, that those higher electrons comes back to the Fermi level, Landau level which resides on the Fermi level in this second case. And so whenever this kind of thing happens, that there is a depopulation happens, we'll have a sharp jump in the density of states. Okay, it attains a peak and then jumps, and this keeps increasing. I mean, as we keep increasing the magnetic field, this keeps happening, and there are a lot of Landau levels. There are a lot of degeneracy in each Landau levels, and basically these things can happen without any issue. So this explains. So this also shows that initially I had 3 Landau levels within Fermi energy, and we have 2 Landau levels now, and the last Landau level exactly coincides with the Fermi energy, and then at B3 we have only 1 Landau level, and that means only 1 Landau level is occupied. So I hope this explains that how the depopulation happens from the higher Landau level to the lower Landau level, and consequently we will get a jump in the density of state, because this Landau level will then be empty, and because of this there will be decrease in the density of state, sudden decrease in the density of state. So I mean, so if you have any question, please ask, then we will move forward.
Hello.
Yes, yes. Oh.
So in 2D electron gas, as we have seen, like this, because of this disorder present, like when we are increasing this magnetic field, it don't have any effect on the plateau actually due to disorder.
Right, right. Hmm.
So here also some similar thing happens, or
No,
it
those
doesn't.
are there are, I think, two little bit different things. I mean, they are related also. So I was going by your that mail that you want to understand the
That
Shubnikov-Diaz
Subnikov
oscillation.
Dihar.
Now,
Yes, yes, yes.
Shubnikov-Diaz oscillation actually explains the oscillation in the longitudinal resistivity. Okay, there are two things: oscillation in the
Yes, yes.
resistivity, oscillation in the transverse resistivity, which is the quantum Hall effect.
Okay,
And Shubnikov-Diaz oscillation explains the longitudinal part. Now, what you are saying is
okay.
correct, that in order to observe the quantum Hall effect, we need to have some
Yes,
disorder. In fact, those broadening or not broadening, those plateaux are stabilized, or plateaus are there because of the disorder. That
yes.
doesn't that doesn't mean you have a very disordered sample and you will get to see quantum Hall effect. No, you'll not see. But if there are
Yeah.
little bit amount of disorder, then you will see. And the reason it happens is because broadening of the Landau levels. Okay, that I will
Okay.
explain once I finish this one, qualitatively,
Okay.
not
Okay.
mathematics. But yeah, so so
Okay.
this
Okay.
is clear, right? Why this
Yeah. Yeah. Yeah.
depopulation and other things happen. And
Yes. Yes.
okay, so let now there is more mathematics, I think. Yes. So so physically or qualitatively, that's what it happens. Now the conductivity or the resistivity, just the inverse of the conductivity matrix, the resistivity is essentially related to the density of state, right? If we do not have any density of state at some energy, then the electrons will not conduct they, right? That is the point. That is the point of a band insulator, let's say. Because why the band insulator normally do not conduct? Because they do not have any electron at those energy levels, which we can excite by simply giving some electric field, and the electrons will acquire some force and they will start conducting. That's not happening because the electronic energy states are not there at those energy levels, I mean around the Fermi levels. So this is the way to understand that resistivity or conductivity is intimately related to the density of states. Because if we do not have any states at that particular energy, there is nothing. There is no electrons. There is no electrons to conduct also. So once this density of states keep oscillating with the increase of magnetic field, here we have energy, but the magnetic field also give rise to this oscillation because of this physical phenomena that I explained. So this density of states oscillation reflects in the uh, conductivity also. Okay, in the longitudinal resistivity or conductivity, that we can prove by many other many formulas, for example Kubo formalism or semi-classical Boltzmann equation, etc. So the oscillation primarily arises from this density of state oscillation, and this was actually explained by I mean this oscillation and oscillation period, These kind of things are explained by Onsager, so which was based on simply semi-classical Bohr-Sommerfeld quantized equation. What really happens in experiment is that uh, we have curves like let's see if we have, yeah. So we have curves like this. If you plot resistance with respect to 1 by b, here we are referring to other things, but let's just focus on what I am saying, that the resistance will increase and decrease and increase and again decrease. If you take this period between two consecutive peaks, two consecutive dips, you will see that this is constant in 1 by b. Okay, so in 1 by b this is constant. That is what was explained by Onsager, and that constant thing is represented or actually uh, presents some valuable information which presents the extremal cross section of the Fermi surface area. That's why it is very important to study the Subnikov-Diaz oscillation of metals. So that was the physics of it. There are a lot of mathematics around which we can say more quantitatively things, but yeah. Okay, so now let's come back to your question of sorry, two. Okay. Now what you are saying, the role of disorder in the uh, quantum Hall plateaus, right? We have let's say rho xy, and we have something like this, some plateaus and then again plateaus magnetic field. Now, if let's think of the simple, so these are energy levels, magnetic field. We have some energy levels, let's say perfectly flat for 2D electron gas. Now, this is let's say along B direction, or no, not B. This is K, just independent of K. Sorry. So okay, so if the Landau levels are perfectly flat, which we have seen that h is simply given by h bar square k square by 2m, and if we quantize that, we get energy En equal to n plus half h bar omega c, right, with omega c equal to Eb by m. So these are perfectly flat. This is let's say n equal to 0, n equal to 1, n equal to 2, n equal to 3, and so on, and they are equidistant. So if there is only perfectly flat Landau levels, then these plateau will not stabilize. Uh, the reason I just explained, ki, again, so there is a direct connection between what I have just explained to I mean in the case of Subnikov-Diaz oscillation, the longitudinal resistivity oscillation, but the things happen similar here also. Here also the depopulation happens. So let's say I have a Fermi energy somewhere here, EF, right? And as you increase the magnetic field, n equal to 1 go higher, n equal to 2 go higher, n equal to 3 go higher, so is the n equal to 0. Now there is, here in this system also there will be oscillation of DOS that will also affect the quantum Hall effect. Okay, it is not really a completely unrelated phenomena, but for quantum Hall effect, to explain quantum Hall effect, we need something else, not only that Subnikov-Diaz phenomena. That's what my point. You need extra things to explain the quantum Hall effect. The only Subnikov-Diaz oscillation thing will not explain things, the features of quantum Hall effect, the stabilization, and so on. So if these are perfectly flat things, I mean perfectly flat Landau levels, then what will really happen is that uh, we'll have some resistance, let's say, and we increase resistance, and then there will be some kind of discontinuity, and then immediately it will decrease, immediately again decrease, sorry, increase or decrease, whatever, increase, let's say, it will go on without having a clear cut plateau in this magnetic field window. Now whenever we have a disorder actually broadens the Landau level, so the sharpness goes away with the disorder. So we in a extremely clean, perfectly clean system, we had the energy level at this energy n equal to 0, which is simply E0 equal to h bar omega c by 2. So this is a single line, right? At this energy we have some zeroth states and corresponding electrons. Now this is a perfectly line. So once I hit that energy, this energy level, and cross, immediately we will go some higher resistance, let's say. But in presence of disorder, what happens is that this Landau levels, instead of a perfect line, it happens to be some spread, okay, some spread. And because of these spreads, the, let's say, Fermi surface is traversing the Landau level. So I have some Landau level initially, and I have some spread due to disorder, and then this is my Fermi energy, let's say. This is my Fermi energy. So EF, okay, this is along the En, and this is, let's say, K. Now this Fermi energy, as the, and let's say we are increasing the magnetic field. So as the Fermi energy lies in this energy range, then it will take some time. That means it will have some spread in the magnetic field. I started with B0, ended at B1, and that is the point where I ended up here, let's say, right? Fermi energy remains there, but actually I should not draw this, rather the state goes higher, so state will go higher. So it's kind of become like this, Fermi energy, let's say, constant, right? So as you increase the magnetic field, state goes at higher and higher energy, gaps increases. So it started here, and whenever we have hit this kind of thing, then this level just crosses the Fermi energy. So there is no conduction happening. All the electrons will come back to the next Landau level, and so on. Next means somewhere here, let's say, another Landau level. So this spread in the magnetic field is actually explain this thing. Again, this is a very vague and kind of only physically motivated. There are calculation and there are more rigorous things, not only this simple thing. But this is the way to understand that why do we have plateaus, okay?
Sir, I think the simplest way that Sir tells about
Mm.
that in the band, the electron or charge carrier is freely moved.
Right.
So resistivity decreases, and after that, suddenly resistivity increases.
Hmm.
Then again the same phenomenon.
So here actually do not decrease, right? I mean, it just keeps increasing, but somewhere it just plateau are there in the quantum hall, at least.
Yes.
In the longitudinal resistivity, we have some this kind of plot, let's say, this kind of plot, right? This kind of plot. It decreases, increases, and decreases. But for quantum Hall effect, it actually keeps increasing with the magnetic field, right? Or if you can think other way, it will also start decreasing like this. You're traversing this direction or this direction. That is the point. So I hope this was clear, right?
Yes.
Hello.
Uh-huh.
Can I ask a question?
Yes, yes, sure.
As I understood, is like this Shubnikov-Dehos oscillation is happening in that longitudinal direction,
Mm-hmm.
and we are getting the plateau in the transverse direction.
Mm-hmm.
So,
Right.
but both are somehow related to the effect
Yes.
because of the effect of the magnetic field as we increase it.
Right, right. Huh.
So, my question is like how, and we know that this plateau get like robust due to this effect of this disorder.
Right, right.
So my question is like how it is affecting this transverse direction in some way while the longitudinal direction in other way. Like why the same argument does not like go through for that long transfer direction also. Like where is this like something must be extra in this transverse direction which is not there in the longitudinal direction, right? Like uh,
Okay.
so like what I feel like if we consider like there is like this both the direction like this longitudinal as well as
Hmm.
this transverse direction, the effect should have been somewhat similar, or it's not like.
So that's where the difference in the quantum Hall comes. So longitudinal direction, in fact, there is a oscillation in the Hall conductivity as well in normal systems. Okay, in normal system means in lot of system you can see the Subnikov-Diaz oscillation, the
Yeah, yeah.
the oscillation in
Okay,
the
okay.
longitudinal
Quantum.
resistivity, and similarly there will be signature of oscillation in the Hall conductivity as well. But very few systems shows quantum Hall effect. So while they are connected and definitely definitely related to the population depopulation of the Landau levels as the magnetic field increases, but quantum Hall
Okay,
needs other explanation and other physics as well, in
okay,
terms of
okay.
explaining this disorder, and then why there is a plateau. Uh, Again, the plateaus are also like 1 by n e square by h and so on, right? There is a formation of actually
Yeah,
topological edge state. So those things are
okay,
there. Those are rigorous theories are there, which is for the longitudinal case, we do not need any consideration of age state and so on. It will just be any metallic system if you apply magnetic sufficiently high magnetic field, measure longitudinal resistivity, it should have. But if you apply sufficiently high magnetic field and then measure transverse resistivity, you are not going to get quantum Hall effect at least. So there are other restriction and other physics that is there. Those things needs to be formed, especially the age state.
okay. Can I
Hmm.
ask one
Yes,
small
yes,
thing?
sure, sure.
Like, yeah, yeah. Like this B field actually, like when I studied this, came to know about this quantum Hall effect, I was thinking like this because of this B field actually only this transverse direction because of that some transverse direction some force will be there, right? This
Hmm.
Lorentz force.
Right, right.
So, so that's why we are getting this Hall effect, and then because we are also getting this quantum Hall effect. So when today you told that because of this B field only these oscillations are happening, means this B field has some effect in the longitudinal direction also.
Right, right.
So that's what like I am trying to think like okay, like then the way you explain this Sobnikov-Dihas oscillation, then it creates some like confusion. Like then I was thinking like okay, then similar thing why it is not happening in the transverse direction also. So that's why I'm asking this question actually.
Hmm.
Okay, but as you mentioned, like maybe some this because of this age states and in, this
Actually,
disorder, some
there is a
other.
age state formation, especially for the quantum Hall effect actually.
Okay, okay,
So while this is related, but the theory of quantum Hall effect or the understanding of quantum Hall effect cannot be only with the Subnikov-Diaz oscillation, the depopulation and repopulation, let's say, of the lower Landau levels. So that's
okay,
the
okay,
kind of DOS oscillation, but
okay,
there is something beyond that. For example, the quantum
okay.
Hall transport is dissipationless, right? I mean, why
Oh, okay.
you have some dissipationless current? It just doesn't dissipate it because there is no backscattering, or the electron cannot go backward way and so on. All other things are there.
Oh, okay, okay. Okay, understood. Maybe so many things are not known actually to me. That's why maybe
Yes,
these
yes. No,
questions
no. Actually, this is
are coming.
pretty advanced topics, and I think what we are covering and what Sir is covering is that we are just covering the, I mean, the qualitative part of it. Okay, if you notice, we are not going through the rigorous derivation of any of those theories. Not we have not even derived
Yeah,
flow
yeah.
formula. So
Yes, yes.
there are a lot of theories and a lot of complicated stuff. For example, if you start see why quantum Hall effect and other things are very important and very interesting. That is even explored today. I mean till today, as I just told,
Okay.
because this is intimately related to the topology of the system, and topology is not something very easy to understand. At least for me, it is still. I mean, there are a lot of things needs to be understood: topology, edge state, band inversion, and so on.
Okay.
So that and all of those theory, actually rigorous theory, has been developed for quantum Hall effect. It has been quite a few work. At least for 2D system, there are a lot of works. In fact, we are near saturation. Let's say most probably, not sure. For fractional quantum Hall effect, even it is poorly understood. It is not even purely understood in the fractional quantum Hall effect, at least. Uh, so is the quantum Hall effect in three-dimensional system. People used to believe that in three-dimensional system there cannot be any quantum Hall effect. I mean that quantization part will not be there. It will not be robust. That was the point. Ki, just say I increase the magnetic field and there is a plateau, and this is a very uh, robust plateau. Robust in that sense that some people want to describe in the way that the straightest line ever measured in experiment. That was the one of the most sophisticated straight line that came out of experiment. Because experiment में क्या होता है? Even if we have a straight line, let's say we will get some straight line, it will be some zigzag will be there. But quantum Hall effect measurement is like experimental data is itself is very accurate if we have correct system and setup. So people believe that in three-dimensional system it will not be stable and it will not be there as such. But there are four theoretical proposal which says that there is something called wild semi-metal. It's a three-dimensional metal. Again, semi-metals means so whenever we have metal, let's say, if you just explain very briefly, we have a metal. We have let's say band one. So this
Okay.
okay. So this is let's say band, and this is Fermi energy. Okay, and Fermi. So these are a lot of electronic states there, right? And
Yeah.
electrons can go there with some excitation and conduct electricity and so on. So this is metal. Now if we have semi-metal, graphene is an example of semi-metal actually. So it's
Okay.
pristine system. Fermi energy lies exactly at the nodal point. Now at this nodal point we do not have any density of states. If you plot density of state of graphene, uh, I hope you have the concept of density of state, but
Yeah.
it
Yeah.
will have something like it will be 0, but I'm not making it 0. Let's say this is, and this something like this actually. It will be symmetric, but okay. Uh, so and this is the Dirac point. Let's say EF, okay, energy equal to 0.
Okay.
And
Okay.
at this point, the density of state almost goes 0. Actually, it goes 0 in a perfect if you do perfect calculation, and start decreasing at somewhere it peaks, which we call Van Hoff singularity (VHS), where the peak lies, and then again it start decreasing. Okay, so this is called semi-metal, where the density of state have a vanishing value at some point of the band structure. Whereas this metal, this will have some if it is parabolic, then you will have density of state proportional to I think EF half, right? So this will start increasing like that. So this is for the parabolic bands, 3D let's say, or 2D 3D. But for graphene, uh, so there is a single point where the DOS actually goes to 0. So this is semi-metal. So similarly, graphene have a simply while semi-metal is just the three-dimensional version of graphene. Again, have similar band structure, nodal point. EF lies at the if EF lies at the 0 point, then we'll have a density of state something like this. This part will be there. It will decrease and goes to 0 and again increase. So in this type of wild semi-metal, there is something called surface state, wild pairs, and so on. Because of this, people started at least putting theories that in principle we can have quantized Hall plateau in even in three-dimensional system, but there needs to be re-engineering in the system. There are a lot of checks and balances that needs to be there.
Okay.
So if you have any questions, let me, let us.
Okay. So maybe not from this
Hmm.
previous thing, but uh, this spin Hall effect, which was the
Hmm.
topic of this week, I think.
Right, right.
So this thing, this spin orbit coupling and this Hall effect, can you just briefly just explain so that it would be helpful to solve the assignments also like this week?
Okay. Uh, so spin orbit coupling, I think Basu explained quite well. So what really happens is that in some material, so actually in every material we have spin orbit coupling. Okay, this is not something that in this material it will be there, it will not be there. The question is not it is there or not there. The question is it relevant even to consider? For example, uh,
Okay.
for example, for graphene, spin orbit coupling is there like other materials, but it is very small. I mean, so energy is I think 10 to the power minus 6 eV. Okay, SOC in graphene of the order of, okay, not exact. And this is, it
Okay.
turns out that this is pretty low, quite low actually. 10 to the power minus 3 ev is still okay, it is in the mev range. Our energy range or the mesoscopic, most of the mesoscopic measurement that happens in condensed matter system, transport measurement at least, consider this mev range. So this is still considerable, but 10 to the power 3 orders of smaller spin orbit coupling than this energy, it almost shows no effect. Actually experiment cannot even detect properly. uh, so every material had some spin orbit coupling. We consider only those cases where the spin orbit coupling, let's say again, this is a rough number, of the order of MeV or higher. Okay, then it
Okay.
actually becomes relevant for the study. I mean, it affects the transport, it affects the other things as well, even optics as well. So,
Okay.
and the reason that every material have some amount of spin orbit coupling, whatever small is this, this can be understood from, again, I'm just repeating what Bosu said, that we have some positively charged nucleus and we have some negatively charged electrons, right? Lot of other orbits are there. Now, we write Hamiltonian, we have some Hamiltonian, let's say it was p square by 2m and so on. Now, this is the orbital motion of electron, right? It represents the orbital motion of
Yes.
electrons, let's say. And now what really happens if we see electrons rest frame, that means this was our initial frame, let's say, right? And so spin orbit coupling actually considers the term that what electron experiences within the atom or within the solid state system, let's say. This also this actually considered in terms of spin orbit coupling. So for electron, if you sit in the electron's rest frame, then it will turn out that everything else is moving, right? Apart from that electron itself. It is kind of experience which we get when we sit in the train and we think that everything else is moving, kind of, sometimes. So these electrons, in the rest frame of the electrons, will feel that the protons are moving around them. If a charged particle moves, then classical theory of electromagnetism itself says that there will be magnetic field as well as electric field, right? A moving charged particle creates both. Again, Maxwell's equation. Magnetic
Yes.
field and electric field are kind of, they are related to each other in Maxwell's equation. Whenever there is a moving charged particle, we are not going the magnetostatics, we are going electromagnetism. So that's why there is a equivalence of magnetic field and electric field. So because of this proton's motion, charged particles motion, electron will feel an effective magnetic field in its rest frame. This is, so there will be some effective magnetic field which will have some expression, let's say classically, using classical electrodynamics, Professor Bosu derived, which comes out to be B effective equal to minus mu 0 by 4 pi. Q is the electronic charge, V cross R, and RQ. R is, let's say, this part. we have a positively charged, and this is r, and this is velocity, let's say linear velocity, and so on. So this effective magnetic field will also create some electric field, right? Corresponding electric field, again going by the Maxwell's equation for electromagnetism, r cube. This will be the electric field, and we can write that effective magnetic field effective as minus mu 0 epsilon 0 v cross E. This is to write v cross E by c square, and this electric field again will convert this electric field, let's say 1 by c square negative, and then v will write as momentum of electron by m, and cross we can also write v equal to sorry, momentum is h bar k, right? So we can also write this, but electric field is simply given by z e by r cube r, or rather we can also take r square. This is cap unit vector, right? And that z e is the, so z is the proton number and E is the electronic charge, and from this we actually come to this z e by mc square r cube. So I'm not deriving because the derivation is already there. Okay, I'm just explaining a little bit more. So minus z e by mc square r cube L. L is the linear angular momentum. So P
Okay.
cross R or R cross P, let's say, whatever. Just there will be a sign change equivalent to P cross R. So this is the magnetic field, and so this is the effective magnetic field that an electron experiences, right?
Okay. Yes.
This part is sort of purely, you can think of classical, right? We have not anything used anything quantum per se. It is
Yeah.
still the classical electromagnetism, simple. Now comes to the
Yes.
quantum part, that in a magnetic, so electrons have intrinsic spin which we cannot understand in terms of any classical analog. So electrons have intrinsic spin and correspondingly spin angular momentum. Again, this do not have any analog, so I'll just say, but the statement will be the following: ki, similar to the angular momentum in classical mechanics, let's say I have a particle, not necessarily electron, and it rotates in some circular motion. So it will have some velocity, linear velocity, let's say, and similarly equivalent to linear momentum, right? Just mv, and it will have some L. So if the circular motion is happening in this plane, and this is, let's say, the outer plane of this board or page, then there will be some L. L is the linear momentum, R cross P, let's say, right? So this is the classical notion, which also happens to be the case for electrons, because it has some angular momentum as well. So this is angular. As we know from the Bohr theory that angular momentum should be quantized in units of nh and so on. In orbital motion, this is already there. Now similar to this, an electron, let's say, simultaneously also have another intrinsic quantity called intrinsic spin angular momentum. That was, I think, first confirmed by Stern-Gerlach experiment, and there is already other experiment, but Stern-Gerlach experiment is famous for explicitly explaining this thing in more lucrative way. So there is something
Yes.
called intrinsic spin angular momentum, which is some intrinsic property of the electron which we cannot think classically. So you just take this analog that similar to L, we have another quantity associated with electron is the S. S is the spin angular momentum, which can be written as h bar by 2 sigma. Sigma is the Pauli matrices. And note that this h bar has a unit of angular momentum, right? H is simply h bar into 2 pi, so same unit. So this is another now,
Yes.
so this we have for any electrons. And let me tell you another point which I think today itself I mentioned earlier, that uh, so in Schrodinger equation, so this is a Schrodinger equation, let's say, right? In Schrodinger equation, we do not have any concept of spin and so on. It doesn't mention anything spin and so on. Psi r is just some wave function representing a quantum particle. There, if you want to say that write the Schrodinger Hamiltonian for spin up and spin down and so on, you need to additionally put the information as spin, right, explicitly. You need to force it, kind of. This is for the Schrodinger equation. But for the Dirac equation, when you do Hamiltonian or Dirac Hamiltonian, right, alpha p dot c, let's say, and some beta m0 c square, alpha beta is some matrices, Dirac matrices, let's say. So there you will, so if you do relativistic quantum mechanics, then you'll see that the concept of spin automatically comes. Here it is kind of motivated from the experiment, motivated from the observation and so on. But from this Dirac Hamiltonian or Dirac theory of quantum mechanics, you will automatically kind of get two state of an electron, spin up and spin down. So spin is intrinsically coupled or taken into account in the Dirac or relativistic quantum mechanics. Okay, so this was a side note, but the point is key, we have two ingredients. One is this effective magnetic field that an electron experiences, and second ingredient is this one, spin angular momentum. And because of these two, it turns out that there is a correction to the energy, or in presence of a magnetic field, an electron due to the spin experiences some force or energy, let's say, and that energy is given by minus mu dot b. Okay, and this mu is the magnetic moment of electrons, spin magnetic moment of electrons, which is given by g e by 2m and s, let's say. And the reason it happens is any, so you are, whenever you are applying kind of magnetic field, you are perturbating the system, and the spins want to align along the magnetic field. So this is magnetic field, this is s, because the energy then it reduces to minus mu b, right, if they are,
Yes.
if they are not aligned or anti-parallel, let's say. So this is, let's say, s and this is b and s, then it will be mu b. Sorry. So mu b, so we have minus mu b and plus mu b. So this is higher energy. So electrons wants to align itself along the magnetic field, and this is the interaction with the magnetic field of the spin angular momentum of electrons. And you just need to put g e by 2m s dot this b effective, which is the intrinsic magnetic field that an electron experiences. So it will be z e, I think there is a minus in minus jd, minus jd m c square r cube, l is the angular momentum, orbital angular momentum. So okay, so this was actually orbital angular momentum. Orbital because this was coming from this orbital motion. Spin angular momentum because this is intrinsic to the spin. There is no analog of this spin angular momentum to the connecting to the orbital. And if you do little bit of calculation, you'll get z e square m square c square r cube l dot s h. So this is we call sometimes Z-man, or better to call it actually spin orbit coupling, HSOC. Okay, so this is the correction to the energy one need to consider due to the intrinsic angular momentum of spin and the magnetic field that an electron experiences due to the proton. And so this is called spin orbit coupling. And as the name suggests, so this is a coupling between orbital motion. So L is coming due to orbital motion and S is the spin part. So that's why you call it spin orbit coupling. And you notice that this is proportional to Z, right? That means as my proton number is increasing, this spin orbit coupling part will also increase. So for light atoms, light means proton numbers are small, so is the mass of the whole atom, because most of the mass comes from the proton itself for an electron, sorry, for an atomic system. So for light atoms, this will be small, spin orbit coupling is small, and as you go heavier atoms, for example W, and then there are a lot of other materials. So as you go higher in the periodic table, you will have higher and higher Z. So is the spin orbit coupling state. There we cannot neglect the spin orbit coupling. And if you notice the carbon it is just 6, and it has an order of 10 to the power minus 6 eV of spin orbit coupling. Okay, so that's the brief of spin orbit coupling and why it arises. I didn't do any mathematics, but why it actually happens. Okay.
Okay, can I ask one question?
You can always ask
Uh,
questions.
yeah, okay, thanks. So anyway, I understood this treatment. I was just wondering, like, this treatment seems so much like classical rather than quantum, actually. So
That's a valid point. There are calculation using the quantum mechanics, and it turns out
yeah.
that there is only correction factor of 2, which is called gyromagnetic ratio. Here we have written, I think, this G.
Oh, okay, okay,
So conventional way we will think E by 2m is angular momentum simply, okay, magnetic
yeah,
moment due to the spin angular
okay,
momentum of electrons. This is just by comparing just with the L, orbital angular momentum, because
okay,
orbital angular momentum also give rise to some magnetic moment, right? If a charged particle is moving, we
yeah,
can think of it is a current. If it is a current, then it will give rise to some magnetic moment, M, let's say, right? Again, classical electrodynamics. So people did this with the, I mean, comparison with the classical model, and later again we need to go back to the Dirac relativistic quantum mechanics. And from the relativistic quantum mechanics also, sophisticated calculation shows that I mean, the expressions are quite correct, except a factor of
okay.
G, which is for free electron it becomes 2, but it is not a universal parameter. If the electron is of some solid state system, which we are interested in, it often deviates from 2 actually by
Oh, so the
margin.
okay, so this G factor is actually capturing that essence of that
Essence of the quantum
extra.
mechanics.
Okay, okay.
Actually,
So
everything is
okay, I
quantum mechanics.
understood.
We are just classically treating. So, as I said,
Yeah,
spin we treated kind of extra forceful way, right? A spin we explicit way
yeah,
in the Schrodinger equation.
yeah,
But in the real relativistic quantum mechanics, it turns out that it is already there. I mean, the formulation itself includes automatically.
yeah. Like
Here also
how
same thing.
I
Hmm.
okay, how I understood like previously spin is like it would automatically come up like if we one consider this Dirac's postulates for quantum
Right,
mechanics.
right. Exactly.
So
That is the
from
point.
there, like yeah, those like from there these things come. So I was actually expecting this spin orbit coupling also to somehow related to that Dirac's postulates, and from there through this quantum field theory, I think it might be coming actually
Yes,
somehow.
yes,
So
that also comes, and this correction automatically gets
that
included.
G factor, as you are
Uh,
telling.
right.
Okay,
Classically, we have
understood.
to nitpick things, and again, it needs to be matched against the those exact calculations. Okay.
Okay.
Okay. So, any other spin Hall effect related question or what?
Yeah, like spin hall effect. Actually, I haven't yet gone through these Professor Basu's lectures, but anyway, I thought that like before I'm doing the assignments, like the next tutorial will be like again 1 week after, right? So so that's why like I if I get some overview before like going through this Professor Basu's lecture, like it would be helpful actually while following Professor Basu's lecture as well actually.
Okay.
So
So,
so because the tutorials are happening actually before this some 4 5 days, so that's why I was thinking
so they
like
do not give 7 days.
yeah yes
Okay. So, spin Hall effect is again due to this intrinsic spin angular momentum, and uh, So what really happens in charge Hall effect? So we have a sample, and just think of not quantum Hall effect, simple classical Hall effect.
Okay.
Z direction magnetic field, and there will be some more electron accumulation in this direction, let's say because of Lorentz force, and combined electric field is there, and in Z direction magnetic field is there, and because of this magnetic field there will be some kind of more electron deviates, like for I mean as if in this direction, and there will be effective positive charge along this direction, right? So it's
Yeah.
kind of charge getting separated and accumulated at the two edge of the sample. And if we measure the corresponding voltage by some voltmeter, we will have some Hall voltage, right? So that's what the
Yeah.
charge Hall effect.
Yes.
Now, spin Hall effect is something where I have a system, let's say, I send some charge current, which you always can do by applying external bias in the system, battery, let's say, simplest thing. And so from this, all type of electrons are emanating, spin up, spin down, and in a spin Hall effect, what happens at one edge, let's say this is spin up accumulating, and at the another edge, the spin down, down spins of the electrons are accumulating. Effectively, there is no voltage difference. Okay, so there is no voltage here, because in general, or okay, so in general can be complicated, but in pure spin Hall effect, the number of electrons in this side and number of electrons in this side in the opposite edges are exactly same. Here the electrons number was differing, that's why we get electric voltage. Here the voltage will not be developed, there will be no voltage, just the opposite
Okay.
spin will be accumulated, and there will be no voltage, and there will be no current direction also. In this direction there will be no current. So this is called the
Okay.
spin Hall effect, accumulation of opposite spin in opposite direction of the of a sample. And in conventional measurement, of course, we cannot measure. There is something called magneto-optical Kerr spectroscopy. This is one of the way, and more easiest way is the inverse spin Hall effect. So this, what we do to measure this actually, so we send a charge current, created a spin current, let's say, or spin Hall effect. Basically, the motion of spins, here in this direction it is up, in this opposite direction it is down, and to measure this we send another spin polarized current in the same sample. And this spin polarized current not necessarily we can send by bias. In fact, it cannot be sent by bias. It is sent through some heavy metals which have strong spin orbit coupling, which will have already I mean spin polarized current, let's say. And these currents we send, spin polarized current, spin polarized current we send, and because of this spin polarized current, now then electrons start moving from this direction to this direction, let's say. Now there is a voltage difference. Okay, so initially the electrons were same, but after you send this spin polarized current, there will be disbalance in the number of electrons in the both side, and immediately there will be uh, voltage difference. So that's how we measure the spin Hall effect. Yeah, question.
Yeah. What is this spin polarized current? Like I'm hearing this for the first time, I
Mhm.
think.
So spin polarized current, we can simply think that a electric current, let's say,
Yeah.
think simplest thing, electric current with more up spins than down spins. So we have lot of electrons going through, right? Whenever we pass
Okay.
electric current. Now it turns out
Yeah.
that we can create some electric current where there will be a lot of electrons, but effectively there will be more up electrons than the down electrons. It's kind of like that. Okay.
Oh.
And this is again related to the spin Hall effect or spin orbit coupling. So
Okay. Okay.
there's something related to spin, we need another spin related phenomena. in the inverse spin Hall effect case. Okay, just because we want to measure this amount of spin Hall effect generated by measuring the electric voltage. That was the difficulty, that uh, in spin Hall effect, in pure spin Hall effect, you don't get any voltage. So to create the disbalance of electrons, you need another spin polarized current. So this is one way, and another way is optical way is magneto-optical Kerr effect, where if I say very
Okay.
shortly and simply, we, I mean, illuminate or irradiate some circularly polarized light, or no, I mean some polarized light, let's say, and because of magnetization means magnetic moments of spins. Okay, so there are some magnetic moments, spin angular momentum associated, and the associated spin magnetic moment is also there, intrinsic to the spins. So because of those magnetic moments, I mean interaction between the light that I'm sending or irradiating and the spin angular momentum that has been accumulated on the edges of the sample, the polarization direction of the light changes. Okay, and that we measure how much it is changing, how much it is rotating, and from that there is a indirect I mean estimation that how much spin Hall effect or spin current has been generated.
Okay, so if I have understood it correctly, like this spin polarized current is somehow creating this disbalance so that we can get a voltage.
Right, right. Hmm.
Okay, so it's like some probe we are like uh, giving to the system in order to get that
Right.
voltage.
You just want to create this balance of electrons in the opposite edges, and
Okay, okay.
there is basically some interaction goes on when you send spin polarized current. It
Yeah.
interacts with the spin angular momentum of the opposite edges, and because of those interaction, uh, let's say up electrons goes down in the opposite edges, and so on.
So this spin polarized current, whether like we'll be when we'll be sending, whether we will make some polarization like the way we want it, and then we will be sending it.
Uh,
Uh,
Minute details of experiment I do not have any very clear idea, but what really does is this kind of experiments are done in some heterostructure, or let's say combined material. So this is one material where spin Hall effect is generated. So spin Hall effect is
okay,
generated, and then below we attach another heavy metal. So heavy metal, in heavy metal spin
okay,
orbit coupling strength is quite high. Z is also high, the atomic number,
okay,
and from
okay,
this also we send spin current here, spin polarized current here, and after that we measure spin Hall effect of this initial or the original device, let's say.
okay, okay, okay.
Okay, so any more questions?
Yeah, no, I think till 8 o'clock only we had this session, right?
Yes, yes.
Yeah, 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 yeah. Anyway, thank you. Thanks a lot. Like,
Yeah.
really cleared so many things.
This is our job. But anyway, as I think if you people are joined, then things become more interesting.
Yeah, yeah. Actually, Friday joining is little bit difficult. Actually, like I have to come from somewhere. Actually, like where I am working, so it becomes late actually to come.
Mhm.
So it becomes little bit late to join. Actually, that's why mostly around 6:30 only I could join actually.
No, no, no
But
issue. You already get the recording, so no issue.
yes, 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 yes. Actually, I will go
And
through that initial part
if
actually.
you have questions, then you can also send me email and we can discuss accordingly.
Yeah, yeah. Okay, okay.
Okay.
Anyway, thank you, sir. Yeah, yeah,
Okay, yeah, yeah, welcome. Thank you for joining. I'm ending the
yeah.